Next subject, transformations. Here are just a few reasons why we use transformations, but the main idea in all of them is that in real-time computer graphics, we want to be able to take a model that's kind of drawn in its own coordinate system where it's centered in the middle of the coordinate system, but we want to take this object and we want to draw it positioned anywhere and oriented in any way in our big 3D world, in our global coordinate system. Or we want to draw multiple instances of the same model in different places, but we don't want to have to actually calculate or think about calculating ourselves different points for the primitives of the model. So we want to be able to set up a transformation that the entire model is sent through, so the entire model is scaled, rotated, and positioned differently. Just a few examples of transformations. A being a map that's translated a bit to the side and down. B being the same map except scaled differently. C is a rotated version of that map, and D is a sheared version. Shearing not being something that we'll use much in real-time graphics, but it's nice to know how it works in relation to the transformation matrix. So here are examples of transformations. In both cases, a house has been scaled, translated, and rotated, and we want to basically look at how this is done and in which order we need to do this to get the final image that we want. In this case, a very simple model with a few points has been used 12 times in order to make a composite image, each time rotating or translating or flipping it differently. So we're looking at a part of the OpenGL graphics pipeline here. Basically CT standing for current transformation. And what we're looking at is that this part, this current transformation, a very simplified version of what we're usually looking at as our transformation matrices. We have the points that we send in, the points of the house as it is on the left, where the house has been drawn in the center of its own coordinate system with its bottom left corner in the center and everything else built from that. And those are the points that we're sending into the transformation. The points that we get out are the points for the house where we want it to be positioned in the end in this global coordinate system, where it's been moved, rotated, scaled, so on and so forth. So the points P1 and P2 are the points in the model in its local coordinate frame. Current transformation describes the translation, rotation, and scaling that we want to do to the house, and the points Q1 and Q2 and so on and so forth are the points in the house when it has been rotated. So the points that we actually want to draw in OpenGL's global coordinate system. So here's a little bit of an introduction to homogeneous coordinates. We're looking at 3D points and 3D vectors here. So points and vectors simply had or have x, y, and z coordinates, and this is the way that we've represented them until now. And the difference between a point and a vector is simply that we say one is a point and the other is a vector. Now we're actually going to make a real distinction between the two by saying, in order to use 4x4 transformation matrices to transform these points and vectors, we actually need a 4-row column matrix in order to do the calculation. So we need to add one row, we need to add one coordinate, and we use this chance to actually make a distinction between points and vectors, where we add 1 when it's a point, we add 0 when it's a vector. And we will see in the calculations that this is not just an arbitrary distinction. This is an actual, has an actual effect on how points are transformed and how vectors are transformed. And this is actually relative or relevant to the way they work. So we have a transformation T of the point P that yields the point Q. And we want to set this up as a matrix. So we have T being a matrix that represents the transformation that we want to do to P and yields the points Q. So here we have a slide that represents basically what we can do with 2D points and 3x3 matrices, transformation matrices, and we're basically setting up the point Q, or the coordinates, x and y coordinates of the point Q, as linear combinations of the coordinates x and y coordinates from P, meaning that we take some kind of scaled version or multiplied version of the x coordinates, add it to the y coordinates multiplied, and then add a constant to that. And this is the only thing that we have to work with our transformations. We have three numerical values, or three variables, that we can use to affect the point P in order to yield the point Q. And set up in a matrix, we simply set it up like this. So the bottom row in the matrix, in the kind of transformations that we're going to be doing, will always be 0, 0, 1. And so in this case, we'll end up with the x values for Q being m11 times px plus m12 times py plus 1 times m13. And the same for 3 dimensions. We'll look at that later on. And we can see that now that we're transforming a point with this bottom row in the transformation matrix, we'll always end up with 1 as the third added coordinate, meaning that the result will be a point as well, if our description of a point is simply the coordinates with a 1 added at the bottom of a column matrix. So we look at the same thing with a vector, except we see that the same thing will happen, more or less, and seeing as the bottom row in the matrix is 0, 0, 1, we'll end up with a 0 as well. But we can also see that m13 and m23 will actually not have an effect on the resulting vector, because they will both be multiplied with 0. And we'll see later on that this perfectly lines up with the idea that a vector actually doesn't have a position, only has a size and a direction. And so the translation part of the matrix, what is simply added to the coordinates in order to move the position of an object, is not something that we want to affect a vector, because a vector is usually something that represents a direction, either a normal to a plane or something of that sort, and that's not something that we want to actually translate. We only want to rotate, scale, and change the orientation of a vector, but we never actually want to change the position of a vector, because a vector doesn't have one. So here's a random transformation matrix, just to look at how the math works. And on to our different types of transformations. Translation in 2 dimensions is done by setting up a matrix, a 3x3 matrix, that is a unit matrix, apart from the fact that the last column is basically viewed as a transformation point, translation point. So m13 is basically the translation in x, m23 is a translation in y, And so what we end up with when we multiply this matrix with the point P is the resulting point Q will have the x coordinates, which are the x coordinates of P, with the translating factor for x added, and the y values for Q will be the y values for P with the y translating factor added. Simple enough. We're simply moving a point along a vector. So scaling, we've already looked at scaling a vector with a single constant or a single variable, and then the entire vector is scaled with the same number, which gives us a vector that still has the same direction as the original vector. Now we have a way to scale the x coordinates and the y coordinates separately. This is maybe not so common in simulations and games and stuff we're using real-time graphics with. Usually, or the most common way of using this is having the same number for x and y, or sx and sy. But either way, we can scale them differently if that's something we need for a specific application. And what simply happens is sx in this position on the diagonal line in the matrix will be multiplied with the x coordinates of P and put into the x coordinate result. Sy will be multiplied with the y coordinates of P and put into the y coordinates of the result. And here's the third common transformation that is commonly used in simulations and games: rotation. And for now we're just gonna set it forth as this matrix. We can learn that or look it up each time we use it. We don't have to go into exactly the math, but it's fairly simple. It has to do with how a vector is rotated in 2 dimensions. And we simply set it up this way. So the cosine, the negative sign, the sine, and the cosine on these specific points, if we calculate them all for the same corner, and then multiply this matrix with P. P is actually missing in this slide, but you can imagine it there at the right side of the matrix. Then we end up basically multiplying the x and y coordinates of P with the correct variables here, and giving us a result into Q. And this will rotate an entire image in the same way. So the image will end up looking exactly the same. It'll have the same ratios, inner ratios, except it will have been rotated. And it'll be rotated around the center point of the coordinate system that we're working with. Shearing is a different idea, where we're actually affecting the y coordinates of the result with some multiplication of the x coordinates of the original point. So we end up with qx being the x coordinates of the original point plus some multiplication of the y coordinates. And the same if we set up in the lower matrix here. We set up G in this place in order to affect the y coordinates of the result with the x coordinates of the original point. And if we look at the rotation again, we can see that that's kind of a combination of scaling and shearing. But a combination in a way where the shearing and the scaling will keep the ratios of the entire image intact, so we won't get an actual shearing effect. So the idea with a transformation matrix is not only to do these single transformations, because they could just as well be done in calculating functions or whatever other way. The idea with a matrix is that we want to be able to do multiple transformations in a single matrix multiplication, or in a single operation. Meaning that, or in the end, the result is that we can do multiple transformations and as many transformations as we want without the cost per operation, per transformation operation, being more or less depending on how many transformations are loaded up in there. So our transformations are simply added to a transformation matrix, and then this combined transformation is made with a single operation, a single matrix multiplication. So this idea, first rotate, then shear, then double the image in size, which is basically scaling by 2, then translate by some point. We could make a matrix for each transformation, and then we could take the point and multiply it through the rotation matrix and get a result. Take that result and multiply it through the shearing matrix and get a second result. Take that second result and multiply it through the next matrix, and so on and so forth. But what we want to do is to combine the operations first and then multiply the point through it only once. And the reason this is cheaper in the end is because these combined transformations will maybe include up to 10, 20 or more. That'll be actually a lot transformations, whereas the amount of points in a single model, where each point should go through the same transformation because it's part of the same model, they can run in tens of thousands or even hundreds of thousands, the points that we run through the transformation without changing the transformation in between. Meaning that it's much cheaper for us to do the matrix multiplications or the combining of the transformations for the 10 or 20 transformations, and then taking those 100,000 points and multiplying each of them only once through the transformation. Okay, so here are combined transformations. And I actually don't want to emphasize this too much because we think it in a different way when we're using coordinate frames, when we're using our kind of local coordinate frame, global coordinate system idea. But this is the linear algebra approach. Basically, if we take a transformation of P, then take which equals Q, then we take a different transformation, T2 of Q, we get W. That would mean W equals T2 of T1 of P. And if we describe them with matrices, we can set them up in this way, and we see that the combined transformation matrix M should be M2 times M1, when M1 is the transformation that should be done first, and M2 the transformation that should be done second. So flipping the order of the transformations. In the end, we're going to do it differently, or actually we're just going to not flip them. But first we have to kind of get to grips with the idea behind transforming coordinate systems or transforming coordinate frames rather than the idea of transforming points. So this is just, yeah, if we want to add something, we should add it at the left, but OpenGL will actually be adding this at the right. So these two slides, not so hugely important, except for the kind of thought process behind being able to multiply matrices together in order to do both of their transformations in a single matrix multiplication with a point. So here are nice examples of combined transformations that we can still kind of describe in a single sentence. So a rotation always happens around 0. Rotation about an arbitrary point will happen by something like starting by translating the entire thing by minus the coordinates of the point, meaning that you're taking the point and translating it into 0, 0, then rotating around 0, 0, and then translating everything back. Same with scaling from a point, flipping over a sloping line. We have to rotate so that we basically take our transformation, take the line that we're flipping over and rotate it so that it ends up along the x-axis or the y-axis, then flipping over the axis, which is simple, and then rotating everything back. In this way we can describe a transformation like this and then we can make them by taking the basic transformations and combining them into single transformation matrices, which do these more complicated transformations. Here's an interesting way as well to look at the transformation matrix and the columns of the transformation matrix. If we take a coordinate frame, an arbitrary coordinate frame, with some point of origin, M3 here, and axis M1 and M2, we can imagine that when we're drawing into this arbitrary coordinate frame, we start at M3 and then we count the x coordinates for the point we're drawing along M1, counting basically lengths of M1 rather than counting units as we do in the global coordinate system. And for the y coordinates, we're counting basically lengths of M2, lengths and directions of M2 along the other direction for the y coordinates. And the coordinates that we end up with by starting at M3, then counting x times M1 plus y times M2, the point that we end up with there in the global coordinate frame is the point that multiplying xy1 will give us by multiplying that with the coordinate matrix, with the transformation matrix, where the last column is this point of origin. The first column is this imagined x-axis, or the vector A in where we described coordinate frames, and the second column is this imagined y-axis, this arbitrary y-axis. So in this way, we can simply say we have a transformation matrix, which is also a description of the coordinate frame that we're drawing into. So anytime we take a point P, and say the point P is the coordinates in the local coordinate frame, we multiply that with this matrix and we get out the point Q, which is the coordinates for the same point. It's the same point, but it's different coordinates because those are the coordinates for the point in the global coordinate system. Okay, so looking at the same thing in 3D, we simply have a lot more factors here. We have a lot more variables, but it's the same idea. Now we have a 4x4 matrix. The bottom line is always 0, 0, 0, 1 for the type of transformations that we're going to be doing now. And we simply have 4 deep column matrices instead of 3 deep. Meaning that we have the x, y, and z, and then we add 1 for a point. We have the x, y, and z, and then we add a 0 for a vector. And then basically have the same ideas here. Translation is still a unit matrix, except the last column is a point that we're translating by. And if we go back to the idea behind this representing a coordinate frame, then we can see that a translation matrix simply describes a coordinate frame that has axes which are the same length and orientation as the axis of the global coordinate system. Simply y, j, and k, 1, 0, 0, 0, 1, 0, and 0, 0, 1 for the x, y, and z axis. The axes are unchanged and they're oriented the same way, so they're parallel to their counterparts in the global coordinate system. The only thing that's changed is the point of origin. So translation is simply a change of point of origin in the coordinate frame that we're drawing into. If we look at scaling in the same way, we look at the diagonal line here, and we have a coordinate frame that has the same point of origin, still centered in 0. We can look at that at the rightmost column. And the vectors, the 3 vectors, are oriented the same way as their counterparts in the global coordinate system, but they're scaled. They're just shorter or longer versions of the x, y, and z axis in the global coordinate system. If we imagine that this is the only transformation that's being done, and this transformation will always relate to the previous coordinate system that it's added to. So in the end, if we add this kind of transformation to a coordinate system, it doesn't matter how its axes are oriented before, they will still be oriented in the same way. They will only be either longer or shorter, depending on the scaling factors. Rotation is a little bit more complicated because we can rotate in endless degrees or around endless imagined axes in 3 dimensions, whereas in 2 dimensions we can really only rotate in this one plane that we have. But in 3D we can have any plane and we can rotate within any plane. But we're just going to look at the rotations around the axis of the coordinate system. Because if we want any other rotation, we know that we can combine transformations by simply rotating the coordinate system in a way that its x-axis is oriented in a specific way. Then we can rotate around that new axis, and then we can maybe rotate back, and then we get a rotation that is around any vector. But for now we're going to rotate around the x-axis, the y-axis, and the z-axis. And the z-axis is probably the simplest way to look at it first, because that's just exact same thing as rotation in 2 dimensions. We can see that when we multiply this with a point, the z coordinates of the result won't be affected, and the z coordinates of the original vector won't be used, because the third row and the third column are simply from the identity matrix. Then we have cosine minus sine, sine and cosine in exactly the same places, because rotating around the x-axis means the same as rotating in the xy plane, which is the same plane as we're using in 2 dimensions. Around the x-axis it looks exactly the same, except the x-axis is not being affected or used as an effect, because rotating around the x-axis means rotating in the yz plane, affecting only the y and z coordinates. The y-axis looks like it's different, because the minus sign is in the bottom left corner rather than in the top right one. But it's not different at all, because we can imagine that it was moved from the x-axis idea. It was moved to the right and down, and simply, as in a circle buffer, just flipped over, because we're only using that 3x3 matrix in the middle to represent this. So the cosine minus sine and sine simply kind of flipped over as in a circle buffer when moved down into the right. That's the way I use to remember this, but you can also just remember that when it's the y-axis, they're not tied together anymore, because it's the y coordinates that aren't being used and aren't being affected, meaning that the second row and second column are part of the unit matrix, and then you simply flip the minus. So shearing is in 3D is not something we're super interested in. It's something that's interesting to kind of look at, just to get the idea, but obviously we have so many different types of shearing. And here are 3 changing x coordinates in the result, using the y coordinates of the original, changing the y coordinates of the result using the z coordinates of the original, and then finally changing the z coordinates using both the x and y coordinates of the original. And then we have endless more options. Okay, looking at the transformation of coordinate frames. This is something that is simply better to kind of describe on the whiteboard, and we'll do that in lectures, and we'll probably do that more than once just to nail this idea in. But the idea is that rather than each transformation being done in relation to the global coordinate system, where if we rotate something, it'll always rotate around this center of the coordinate system, So if we translate something first, we take a point and we translate it out by 2, 3, which means it goes to the right and up. When we rotate it, we're rotating it still around the center of the coordinate system, meaning that it'll simply go in a bigger circle than it would have otherwise. The transformation of coordinate frames works a bit differently because we want to imagine that we're not transforming the point, but we actually don't use the point just yet. We're transforming the coordinate frame first, and when we've done enough transformations of the coordinate frame, then we draw the point into that new coordinate frame, and the result will be new coordinates for the same point. It's the same point in space, except the coordinates we put in are its coordinates in the local coordinate frame, but the coordinates that we get as a result are the coordinates for that point in the global coordinate system. And each transformation is done relative to the coordinate frame that we're working with now. So if we start by moving, transforming, and translating by 2, 3, that means we now have a new point of origin in our coordinate frame, the point 2, 3. Otherwise, the coordinate frame is the same. Now when we do a rotation, what we want to happen, or what we want to imagine happens, is not that the entire thing is both moved in space and rotated, so that it's rotating along a circle with a center in the center of the coordinate system. We want it to rotate around its own center, so imagine that it just rotates exactly where it is, but we're only changing the axis of the coordinate frame that we're working with. We're not changing the point of origin at all. And to achieve this effect, the only thing we need to do is to flip the order in which we multiply matrices together. Because multiplying the rotation first and the translation second will give us a transformation matrix, which, if we're imagining that we're rotating points and transforming, this will look like the point was transformed first, was rotated first, and then translated. But if we're doing it in regards to the transformation matrices for coordinate frames, then the result is that we imagine that it was actually the coordinate frame translated first to a specific spot, then rotated, and the point drawn into those coordinates. And the result that we get out is the coordinates for that same point, except in relation to the global coordinate system. So we have functions to perform these transformations in OpenGL, and we're going to look at just a few of those. The transformation matrix that we're mainly looking at now is the model view matrix of OpenGL, which is the first transformation that every point is sent through. And we can imagine this matrix having some kind of state. That is, we change this matrix by calling OpenGL's transformation functions, and this changes the matrix. If we don't call any more transformation functions, this matrix will be the same until we call them again, meaning that we can now call 100 different points, 100,000 different points, 1,000,000 different points, and they will all be transformed in the same way. So if they're all part of the same model, the entire model will go through the same transformation. If we now want to draw either the same model in a different place, different model, now we can simply clean out the transformations that we had already done, make new transformations with calls to OpenGL's transformation functions, and then draw a different model and send all of those points through that transformation matrix. So when programming, the order is always call all the transformations that we want to use, then draw all the points that we want to be affected, then call all the transformation changes that we want, and then draw all the points that we want to be affected. So we have two different matrices in OpenGL that we're using in this way. We're usually just going to look at or for starters, just look at the model view matrix. We'll look at the projection matrix later on when we look at the camera in better detail. The model view matrix is basically everything that has to do with position and orientation in 3D world. The projection matrix is only anything to do with kind of the lens type of the camera, how we're projecting onto a 2D plane. The projection matrix is what does the transformation from 3D to 2D for us in a perspective projection. So here are three functions to do these basic transformations: translate, scale, and rotate. The rotate one actually takes in an angle in degrees, and then x, y, and z are any arbitrary vector that you want to rotate about. So the basic functions that we're using, we can get those by putting in either 1, 0, 0, 0, 1, 0, or 0, 0, 1, but we can also put in any arbitrary vector there. And OpenGL simply uses a specific type of matrix that rotates around an arbitrary vector. The other ones are fairly simple. It's simply the x, y, and z factors on either the scale or the translation that are the variables. Okay, for OpenGL 1, these are all relevant. But in OpenGL 2 or later, push matrix and pop matrix are something that we kind of have to build ourselves if we want to have the same functionality as they do. However, push matrix and pop matrix make such a nice functionality for doing multiple transformations and accumulating transformations and then backing up, that I include them here and expect us to use them at least for the beginning of the course before we try to do something more complicated. GL load identity simply takes the current matrix and sets it as the identity matrix. So if the last time we called GL matrix mode was with the variable or with the constant model view, that means that load identity will load an identity matrix into the model view matrix, basically cleaning out every other transformation that might have been added. So it's basically a reset of the model view matrix. What push matrix and pop matrix do is they simply take a copy of the current matrix and put it on the top of a stack. Or push matrix puts it on the top of a stack. Pop matrix takes the top matrix off the matrix stack, basically clears it off of the stack and copies its values into the current matrix. So this means that if I want to draw a solar system, I might draw the sun in the center. Then let's say I want to draw Jupiter or some planet that has multiple moons. So what I do now is I rotate for its orbit and I translate to out where Jupiter is. And then I push the matrix there. I draw Jupiter itself in the center. Then I push the matrix that I have. Then I can rotate and translate to the orbit of the first moon, rotate around that, draw that wherever it is. Then I can call pop matrix. And rather than going back to where the sun is and having to start by going to Jupiter and rotating and all that again, I'm already at the center of Jupiter. Next, I rotate and translate for the orbit of the next moon, draw that moon, call pop matrix again. Then I'm back at Jupiter. Then I call push matrix again to keep the matrix at Jupiter's point, go to the next moon, draw it, and then call pop matrix to be back at the center of Jupiter. A nice usage of this is simply that whenever we're drawing a specific object in a specific object's drawing function, we'd like to start by calling push matrix, then doing the drawing function, and then end by calling pop matrix. And have an equal amount of push matrix and pop matrix within that if we're going to different sub-objects of this object. What that means is that the object doesn't need to know of the coordinate frame that has been set up before its drawing function is called. And making sure that GL push matrix and pop matrix are called an equal amount of times means that when the function returns, OpenGL will still have the same coordinate frame as it had before the function started, meaning that the function will not only not have to know how the coordinate frame was before it started, it will also be able to return, basically clean up after itself, return the exactly same coordinate frame as it started with. And it doesn't even have to know what that is, because it simply says, okay, I'm going to take whatever is now here, and I'm going to push it on the top, and in the end I'm going to pop it off, meaning that all of my changes are taken out, but none of the changes that had been done before I was called. So here are projection transformations for affecting the projection matrix. Actually, GLU look at has to do with a camera, but that is not a projection transformation. So GL ortho sets up an orthogonic projection. An orthogonic projection basically works in a way where everything is projected from 3D into 2D without any perspective projection, meaning that things that are far away won't get smaller, things that are close won't get bigger. Everything will just have its same size. And this is used often for viewpoints in architecture or in 3D modeling software and stuff like that, where you just want to see whether things are exactly the same size or how they're related with each other without the distance having an effect. GLU perspective is by far what we use the most in simulations and in computer games in 3D. And GLU perspective actually calls an OpenGL function called GL frustum. But the GLU part kind of allows us to set up a simpler or more intuitive set of variables, having basically a field of view, which is kind of an angle, an aspect ratio, and then a near and a far plane. And we'll look at in more detail how exactly the relationship between this GL utilities function and the original GL function works. So these two, GL ortho and GLU perspective, are setting up our lens. They're setting up how the projection happens in 3 dimensions, or from 3 dimensions into 2 dimensions. GLU look at, on the other hand, is setting up the position and the orientation of the camera. And GLU look at will actually have an effect not on the projection matrix of OpenGL, but on the model view matrix. We're setting up where the camera is, how it's oriented, where it's looking, so on and so forth. And we basically have a point and 2 vectors, or actually 2 points and a vector. The first point being where the camera is, the second point being where the camera is looking at a point, and we can then very simply calculate a vector between those, which is what OpenGL uses onwards. And then we have this up vector, which is not straight up from the camera, but it's kind of up in our world. What is the general up direction in this world? And it's used as an anchor, basically, because if we just have a point where we're at and a point that we're looking at, we could be oriented in any way. We could roll the camera around in any way and it still have the same position and the same point that it's looking at. The up vector anchors that. So even if we're looking down diagonally in like a first-person shooter, our up vector will probably simply be 0, 1, 0. But that's a good enough anchor to stick the camera to being oriented the way we wanted, so that we feel like up is up and down is down. So that's the end of this overview of transformations, both generally transformations in computer graphics and a few functions that we use to perform those transformations in OpenGL.